Interface. So coming to that interface topic. So in last class we have seen that generator and everything, right? So if you observe in the test bench, so there is a component name called as the interface. So which is directly connected to the DUT. So how it will refers is, so this is your entire test bench. So that generator, driver, every component that we are seeing, right? So that will related to the test bench. And your DUT will be there. DUT. So that the TB and the DUT connection in between, that one thing will be there, that is a interface. So normally we have that all input signals and output signals, all that signals, right? So now let's say here this is A, B. So here we are doing a half adder, right? So you have a two output signals from the test bench. Let's see, observe in that TB viewer. So if you observe here, so you have a three signal A, B, and C. So if I'm seeing a point of view of a test bench, A and B are the outputs that are going to that as a inputs to the DUT, and C is the input to the test bench that is coming as the output from the DUT. So whatever that side I'm seeing, so depending on that it varies, right? And suppose now I want to connect the test bench and DUT, right? So the DUT instantiation will do. So that is as usual DUT instantiation. So second thing, so now every time when you are seeing the test after the top module, in the top module we will do the test DUT instantiation. So after that, if you observe, there is a test called another file called test. So that test, in the test also we need to do the instantiation. So the test case, that whatever we are driving, the test case it is there, right? So the test case has to see this all the signals, this A, B, and C, all the signals. So for that, the test instantiation also we need to do. That also we'll do it in a top itself, but that instantiation that we have to do. So now coming to the test cases. So depending on your design, you have a lot of test cases. So let's say example here, A and B is there. So test case means one functionality that we are going to verify. So here it is a simple A and B is there. So we need to drive the values for A and B. So let's say an example of combinations. 0, 1, 1, 0, and 1, 1. So 4 combinations, right? So now if you want to drive these 4 values without any randomization, so these are the 4 separate features. Let's say an example. So now you have a 4 test cases. Now you have a 4 test cases. So these 4 test cases we need to do that test instantiation separately. So total you have to write it 4 times. So here it is a 3 signals, that will be simple. Let's take an example of real IP. So that contains thousands of signals or hundreds of signals. So a lot of signals will be included in each test case, right? So in that test instantiation, so now you are writing, let's say an example, typically of 50 signals are there. So now you have a 10 tests. So that means 500 times instantiation you have to do, right? So 50 times for the test case, each test case you have to do that instantiation, and for the each signal. So this will be a difficult, right? So instead of that, so what we will do is, so we will group the entirely all the signals, that is interface. Now there is a one person called interface. He is sitting in between the test bench and DUT and monitors all the signals transitions. So from the next time, we no need to do this test instantiation. We no need to do this test instantiation. In a single line, we can do that one. DUT instantiation, every time it should be normal, like earlier how we have done. That would be same. Now, this test instantiation we no need to do. Directly from that interface, we can do that one. And there is a lot of advantages regarding that interface is also there. So there is a called clocking block, mod code, the directions we can mention, and that sampling we can do, everything. So that code format is interface name. So here I'm using INTF. Interface INTF. So if you want to create that clock and reset signals, commonly we'll do this clock generation or a clock instantiation we'll do here. So if you want, you can do it here. Bit clock reset. So now what that interface typically it is doing? It is grouping all the signals. So what are the signals? Bit A, bit B, bit, this is 1 down to 0, 2 down to 0. 1 down to and interface. So interface and interface. So I'm not writing here the clocking block and mod code. We'll see that one too. So same thing. Create a one more file. Name interface.sv and write this code. Interface INDF bit clock comma reset bit A bit B bit C. So here I'm not caring about the directions. And whatever the assertions will write, right? All assertions will be here only. In the interface construct, mostly we will write all the assertions. So if you are like already if the designer is writing that assertions, so he will write it as a separate module, assertion module. Using bind keyword, we'll have seen, right? So using that bind keyword, we will take that assertion from the DUT to the test bench. But if new assertions are writing, they will write it in an interface, because interface is the only construct that is seeing all signal transitions. Let's say an example of TB. So from the TB, A and B are going. So it will see the driver will see the A and B values, but it doesn't see the C value, right? So coming to the DUT, so it is taking the signals. So DUT will observe A and B inputs and see whatever the C value. So after output is generation only, it will observe that value. So there is a in between, the DUT has a DUT point of view and TB has a TB point of view. But interface is the only one who monitoring all the signal values and transitions.
Vamsi. Yeah, this testing sensation, right? But why DUT design required our test bench APIs?
Sorry.
No, why design required our test bench APIs?
So let's take an example of the DUT instantiation. Normally, first you have to connect your TB with the DUT, right? Test bench.
Yeah,
So
yeah,
that DUT instantiation we have done. That's clear, right? So
yeah, that is clear.
that we'll do it in the top module as usual. So let's another version. Like here, if you observe A and B that I'm driving, right? So as a feature wise, I'm driving all the signals. So now let's say an example of one feature. or one functionality that you are implementing. So that required a less number of signals. Let's say an example, it requires A and C only signals. So at the time, the test instantiation, you have to do that because that test is the main frame that here we are driving that all the values. So normally we will initiate the test bench from the top module, but actual test bench, I'm saying. So test bench driving will happen from the test class itself. So that
My doubt is for design we no need to drive anything, right? From design itself we will take the inputs, right, to test bench, but we are driving values from test bench to DUT design.
yeah, yeah.
That is not, it will not happen, right, in real time.
No, in real time it happens like the test case is the main frame that we are like we are randomizing, right? So simple an example say in generator as last class we are seeing that randomization, right?
Yeah,
So
once.
that randomization is done, but let's say that randomization is now depending on some particular functionality that we are driving. Okay, so like you have a 10 functionalities. So how you will manage these 10 functionalities? So that randomization you are doing a basic thing, but after that the driver whatever he is doing, or like let's say some particular in one function. Let's say I'm writing two features. Here in this first feature I need a value of a equal to 0. In second feature I need a value of a equal to 1. So how you will configure this? So you can't write a constraint, right? Because if you are writing constraint, it is applicable to all. So now how you are going to configure this a equal to 0 and a equal to 1 in two different features. So that is actually test case. So each test case will verify one particular functionality. So we call it as a test case definition. So if you see the test case definition, it will tell you like what it has to do. So let's say an example here in this test, it has to drive a equal to 0. So that randomization will be restricted from the test case itself. So each test case will see it like a different one. So first test, it is entire different test bench. Second test, it will see that entirely different test bench. So what are the test bench inside it is there, it will use those things. So that is the hardest part here in this system Verilog, but that will be reduced in a UVM. So each and every time, so let test 1 and test 2. So each and every time you need to instantiation to your DUT separately. Because here we are seeing that test bench as a two different things. Understood, right?
Yeah, understood. One more, this DUT and design both are same or DUT is different?
DUT and design both are same. Normally, as a standard, we call this as a DUT, design under test.
Okay.
Understood, right?
Yes, Vamsi. Yeah, yeah.
So next, so for this interface, next time we will create that handle. So interface name, INTA, interface handle, anything you will create. So next time you as per the test instantiation. So no need to write all that signals here again. Directly we will use this I1 as a handle for your entire test instantiation.
In between TB and DUT, there is a transitional packet, is there?
No, that packet that we are sending is that through that interface.
Vamsi, it is which interface, Vamsi?
This is a
Like,
static interface that I'm about to come.
okay.
So now, so if you are observing this one, so this is a static interface. Why this is a static interface is, so this is which is completely related to the DUT side. It is not, if we are saying that one, so we are not yet connected to that our test bench, because our entire test bench is a class based structure, right? So class based structure means which is a complete a virtual memory. So coming to the DUT, which is a static in memory allocation and completely. So this interface is related to the DUT side, which is referred as a pins also. Sometimes let's say in real world, if you are writing an interface, we'll refer this one as a the pins, real pins that we are whatever we are seeing. Okay. So now this is a static interface which is reflecting a standard pin configuration. So which each input what it contains and everything. So coming to this interface, so now you have to connect to your test bench side, right? So this interface will going to be as a visual interface. Visual interface. So that same interface will be there. So we'll take the instantiation of a visual interface. So visual interface. So whatever the interface class name is INTF, right? So INTF, that same that whatever the static interface is there for us. So we'll take that interface name INTF. So we'll create a one handle. Now with that virtual handles, multiple handles we can create now. So that means I am creating a one virtual memory that is configured for the as an interface, that is taken from that test bench side. So that standard interface construct is common. Interface INTF, do whatever the signals and interface. That is a one part. So visual interface that we can take it as a directly handle we can take from the static interface. Yeah. Note down that interface that you have to create a separate file and you have to write that code in it. Continuation to the topic, mod port. The mod port. Keyword itself, it is mod port. So what is the use of this mod port is, so in order to restrict the accessing of a signals, in order to restrict the accessing of a signals, we will use that mod port, or we can say that to know the directions of a signals, to know the directions of a signals. So let's say an example of here the TV. So mod port TV I am writing. So now here A and B are as outputs, right? For output A comma B and input C. So now if you are writing as a mention as a mod port, so now these A and B as the outputs, right? So it will allow to assign the values to that A and B only. That means if you are changing a values of A and B, it will allow. So that means, so directly if you want to access that mod port, so you have to give that path. So INTF, sorry, I1, right? So instantiation name, mod port TV and A. So you can change the value. But if it is coming to as an input and you are trying to change the value, it will throw the error. It will give you the directions of a signals as well as it will give you to the restriction to set the values of a variables. So normally this mod port will write for the driver and a monitor commonly. Driver and monitor. Mod port, driver. So driver is also same here, right? Output A comma B comma input C. Mod port, monitor. All are inputs to the monitor. So there we can't change any values. That you guys will get to know in later class. So this is a common one.
And we will use here only the input to the monitor.
No, all ABCR will be the inputs to the monitor. You want to note down the theory? It restricts the accessing of a variables and it will give you the directions of the signals.
Something.
That's the signals. Then next, clocking block. Clocking block. So coming to this clocking block, so it will give you the information of a sampling of a events or a sampling of a signals here. So that signals when it has to be sampled and the sampling skew it will provide. Skew means here, so here you have a clock signal. So let's take an example of positive clocking event we call it. So before of that passage, at what time we need to consider the signal values. and after. So this is called as an input skew. This will called as a output skew. So if that signal is present before of that input skew and after of that whatever the input skew it will mention, if that signal has a value in this one input skew, that only it will consider that signal. So let's say here the clocking. So clocking block name you can provide. So there will be two clocking blocks, driver clocking block and monitor clocking block. So I'm writing for the driver's clocking block. So at the rate, at what edge you have to sample. That is a clocking event, either positive edge or negative edge. Positive. Next, so there will be default skews are there. If you are not mentioning, that input skew will be considered as a 1. And output is 2. This will be the time scale, time units. So if it is a nanoseconds, input skew is 1 nanosecond and output is 2 nanoseconds. Or otherwise you can mention for that each and every separate to that signal. So here, what are the here? So for the driver I am writing. So what are the output signals here? Input C, output P, and clock. So if you are mentioning as a default skews, so you can change here in input skew to 4 and output skew to whatever your wish. Otherwise, you can mention as a delay to that each and every signal skew. Understood, right? Interface construct. Any doubts in the interface? Online guys, any doubts?
Vamsi, what is the difference between sampling and receive?
Sorry? Sampling and
Receive.
received.
Yeah. So normal data we will receive, right? Once we send the data, we will receive, right? What is difference that receive and this sampling?
So coming to this sampling means, so indirectly we'll say that whatever that value that we are sending, right? So sampling means at what point it is taking that value. So let's say an example of analog and digital. That would be better for sampling. So let's say this is your signal that you are transmitting. So if you observe here, So there is no certain point where you can take the value, right? So that value that it is flowing continuously. So you can't figure it out at a particular point the value. So coming to that sampling means, so here one particular point, maybe whatever it is the point. So at particular point, you are taking the value of that signal. So this is called as a sampling. So here in particular point, we are taking the value of a signal. So similarly here, if you observe, so that sampling is happening at 4 nanoseconds before of that whatever the clock edge. So the clock edge, whatever we are seeing before 4 in 4 nanoseconds, that we have started that sampling that value. So it will consider that value at that point. Similarly, that output skew. So it is sampling till the 2 nanoseconds. That signal has to stay. Indirectly, we are seeing. So that signal, whatever that we are seeing, it should be stable in this configuration. Whatever that input skew and output skew that we have mentioned. Understood about
Okay.
sampling, right? So that is a particular point that we are taking the value in simple terms. Receiving
Yeah,
at
okay.
any point it can be received, right?
Correct.
Any doubts?
So this mod port, we are giving output and input. So we are mentioning the directions.
That let's say example you have here, that's why example I have taken as a TB. So that your mod port now it is a TB one. So for the TB you are taking the direction. So the TB if you are taking the direction, so what are the outputs it is going? So A and B are outputs are going, right? So these are the variables that we are configuring it, because the test bench said A and B values only we are sending it, right? As a output. So that it will allow to change the values of this A and B here. So you can configure, let's say 0, 1, whatever the values that you want. But coming to that here as an input, so it is coming from the outside to me. So I can't change the value of it, right? Because it is an input. So someone already has given that value to that variable. So at that time, we will mention as an input, so that you can't change the value. So it is a restriction to that input C now. So whatever the values that are going outwards, that we can change the value. If you are trying to assign a value to this C variable now, it will throw that error. Because when you observe in our test bench transaction class, there we didn't mention as an input or output. Just we mentioned as a signals, whatever the signals that we have. So there is no directions that we are mentioning here. So that will be one of the problem there. So if you are taking an example of a design, so while we are writing the design, so we clearly mentioned like what are the inputs and what are the output signals, right? So but coming to here, we didn't mention like these are the input signals and these are the output signals.
Vamsi, this mode port comes in interface. I mean, like,
Yeah,
will we?
inside that interface.
Inside interface.
Interface is there, right?
Huh.
So in between, we'll write this clocking block and mod port both.
Okay.
And if you have assertions, we'll mention that assertions as well.
Okay.
So next thing. So here, if you observe that interface signal, so we mentioned as a bit, right? So bit A, bit B, bit C that we are mentioning. So actually, it is a illegal one. So there is how our data types are there, right? So our data types also have a restrictions, like either it would be a input port or output port, right? Example, if you are taking as a reg and wire, so reg and wire can't be supported for the input, right? So reg will be taken as a both input and output, but having a specific configuration. Whenever that it is a continuous assignment comes, then reg fails again, right? So according to the port connection rules, So input side, output side, and in out. So when we are seeing that input side, it will be from outside. It is always as a rich. And it is a wire. For coming to this in out, it is also wire. So these as a standard configuration of a input port connection rules, input and output connection rules. So there it was easy. So rich or wire that we declared in the design. But coming to that system Verilog, so we have a lot of data types, right? Int, bit, whatever it is, logic, everything it is there. So now these whatever the data types that we are seeing, it won't support for all. So anyway, we don't have any directions here. Whether it is an input or output, we don't have any directions in the test. So there we can use whatever the data type it is, right? So but coming to that interface. So if you observe that interface here, which is acting for the both sides, right? It is like a in-out that it is acting. So according to that interface rule, so whatever that bit other data types are there, it won't support all other data types. It will only support only a logic data type. That is the major advantage or major use case of a logic data type. So instead of writing these, we'll write logic A, logic B, and 1 down to 0, logic C. So logic is the only data type that allows in an interface. So this data type, whatever that interface we are seeing that, right? Logic data type. So that data type and system Verilog test bench data type, that can be different. There won't be any problem while connecting. But that sizes should match. Remember that. If sizes are there, it should match. Otherwise, no issue. Whatever the different data types are also there. So logic is the only data type which allows you to write it in an interface. So create a file as we are doing the test bench. So with that interface.sv and write this complete code. Interface and end interface. That is enough. So this mod port and clocking block are not required here. Those are all kind of like a optional here. Because those two are like a restriction, right? Mod port is to restrict the directions. So here we have a less signals A and B and C only, right? So we know that what are the signals that we can opting for the inputs and outputs. If multiple numbers of signals are there, let's say 10 or 20. So in that which are input and which are output, that will be difficult to remember. So at that time we will write these things. Online guys, clear? Any doubts in today's class? So while coming to this interface, so this will stays only one interface in under test bench. So let's say take an example of your test. We have seen the test bench, right? What right in the entire test bench? So we have seen that in agent. Agent contains that driver, monitor, generator, right? So this agent, if you are observing driver, monitor, generator, this is one component that is fixed to that one agent. Let's say you have a transmitter and receiver. So we will multiply these agents. So there we need require two drivers, right? So this will be a transmitter. Let's say an example. So another agent we will configure. Receiver. So for this agent, receiver agent, again, this driver, monitor, generator will be different as a transaction packet also. So these all will be clubbed in a environment. That agents, whatever that we are seeing, the transaction packet, driver, monitor, generator. So these all can be different. But coming to this entire will be in a test bench, right? So this will be passed to one interface construct. Whatever that we are seeing that DB. So here that scoreboard will be single scoreboard will be there. You can split it to multiple, but as a typical one scoreboard is enough. If multiple agents also there. But if your components are increasing like a transmitter receiver or master and slaves. So at that time we'll increase that agents. Irrespective of into respect to that one, that driver, monitor, like that generator, everything will also change separately. For each and every agent, it will be different. So simply that interface will be referred as a bundle of wires that are grouping together. So that supporting data type for that wires is logic. So here in this example, we are seeing only one agent. So that means one driver, one monitor, one generator. It for today. Any doubts, online guys?
Say what driver will do?
Sorry.
Driver.
Yeah, we will see that one tomorrow. That driver
Okay.
monitor mostly will try to complete in that same session.
Hello, Vamsi. So, in a clocking module, right? Clocking driver
Clocking.
CB. So, the default input hash 4, that means before the clock event clock event happens, 4 nanoseconds before that, this input is going
It
to be
will
triggered.
sample the input.
Okay, sample the input. Okay. So, and then hash input C, output A, output B, then how they will behave. Will they behave with 1 nanosecond?
Means if
So,
so if you are mentioning as a default input and output queue,
uh-huh.
so it is applicable for all the
Oh, okay. Fine.
not
Okay.
like a only single one. So it will applicable for all the ABC signals.
Oh, okay.
Unless if you are mentioning separately for each and every signal.
Okay.
That we are going to mention with that single hash you can mention 4 nan. Suppose let's say here 4 picoseconds. So the now it is applicable for the inputs Q will be 4 nanoseconds.
Okay.
So either you can apply as an individual, or if you are applying as a default, it applicable to all entire clocking.
Okay. Yeah. Yes.
And this clocking block also will be different from component. Like here we have taken as a driver, right? So for monitor, we will consider another clocking block. There all the signals will be inputs only.
Okay.
Why all the signals will be input, we'll get to know that next class. Any other doubts? Then you guys can log out. Thank you.